So welcome to my talk. The title is kind of C++ error handling revisited. Now, to get kind of into the scope of error handling is kind of quite a broad field. So I want to kind of give a context of what I'll be talking about today. My context is just kind of to do something interesting for software. Software has to some kind interact with the world around it. If a software is just if it doesn't interact in any way with the outside world, so there is no user interface, there are no sensors, no actors, it's very uninteresting. Then it's the same thing as like a stone. It doesn't do anything that you can observe. So therefore it has to interact with the outside world. And if you do that, then things can go wrong because you cannot control the outside world. And kind of that for the user of your software, that it's a nice experience, you somehow have to handle kind of this unexpected, or maybe it's not even unexpected, these things are also expected, but kind of not the happy path. You have to kind of be able to cope with all these things that can happen. So to make things easier, I maybe start with a little example that we will look at through this talk. Imagine that I have kind of a nice plant in my home, and because now, for example, I'm not at home and I don't know when I can get back because maybe borders are closed. So I want to have an automated watering system, and it just consists of some kind of microcontroller. There are some temperature sensors, there is a moisture sensor, and there is a pump to pump water into kind of the plant. So to water the plant. If I now program this little setup here, it could look something like that. I have kind of this watering function in my program. It reads out the moisture sensor, it reads out the temperature, then it calculates how much water I want to pump into the plant, and then I just pump the amount, and the function also returns kind of the amount it has pumped for maybe the outer layer wants to do some logging or some bookkeeping or whatever. But now all these reading out sensors, like activating the pump, these are stuff that could go wrong. So we need to do something about that. And the patterns that I normally kind of see in code at places that I work is one pattern is kind of this arrow pattern. So I read out the moisture, then ask, could I read it out? Then as next I read out the temperature. Oh, sorry. I look, could I read it out? And then it gets nested and nested and nested and nested, and the more steps you have, kind of the deeper this arrow gets. So this is it's not really nice to read. It's a lot of, and it makes it unreadable a bit. And it's also what I don't really like that much is I have to define this moisture variable, and then I have, before it was returning the moisture, now it returns a bool or something. Yeah, it returns a bool. And to get out the real moisture, I have to use output parameters. Until yesterday, I was very worried about output parameters. Now I'm not so worried anymore. I know it's just partially formed. But I don't really like it, because if you get a false back, what can I tell about the moisture? Maybe I had the moisture from before there, now I call it and then it tells me false. Now is there still the old value in there or not? I don't know. Another pattern is it's maybe kind of the same as before. It still returns a bool and the output value comes as an output parameter. It's just the arrangement is different. It's kind of these early return statements. I ask to do it something. If it goes wrong, I just return, and if not, I go to the next step. And the third often viewed pattern that I see a lot of times is, or not a lot of time, but sometimes it's kind of using the C++ exceptions. The nice stuff about the exception is that the code that you're interested in here, kind of the sequence of these steps is nicely together, and the error handling is kind of at a different place. So it's really nice because that's what you're interested in, maybe, or maybe, yeah, it's kind of separation of concerns a little bit. I don't want to go into the discussion whether using exceptions or not. That's something quite different to talk about. But I have one argue to say why I don't like exception that much. Exceptions are like kind of if you look at the code from a higher level perspective, it's like a break in the flow. It's like a go-to on steroids or something like that. It's really hard to keep track of where does your control flow go to if you have exceptions in your code. Yeah, that's all from C++. So now we can go to nicer, greener fields. So some time ago, I kind of started to read this book here. Learn Your Haskell for Great Good. It's a really nice book. I can really recommend it. If you're taking something home from that talk, it's kind of get this book and read it. You can also read it online. It's freely available online. Yeah, taking pictures. And what I learned there is, if I would implement that same example in Haskell, it might look something like that. Maybe who's seen Haskell code for the first time in his life? So that's like the majority. But if you look at it, can you kind of understand that it's doing maybe more or less the same thing as before? I think it should not be that difficult to kind of understand. Just to look at it, see, it does some read moisture, and it's the error is pointing there, so maybe the moisture gets into this thing that's called moisture, and so on, and the calculate taking the moisture and the temperature and this the amount and pump and return. Now this code maybe just looks that nice because there is no error handling at all. It's like the first example. So what happens if it goes wrong? How does it look there? So the good message is it's already there, the error handling. But now I can say, yeah, I mean, if there is error handling there, I should kind of see that there is error handling there, because if not, then it's like the exceptions, it's very implicit, and I have to search maybe a lot to find out where is the error handling. But if you're a Haskell programmer, you see it immediately that there is some error handling, because if I just look the upper part, kind of the name of the function, and this colon, this is kind of the definition of the function or declaration. It's just the signature. And there is something, it states it will return a maybe volume. So it says, I maybe return a volume, but maybe I don't return something. So this already tells us there could be something that could go wrong. And then the second thing is that the function starts with this do. Now, maybe because we're C++ programmers, for us do is like a normal statement. In Haskell, it's something completely different. And it's, for the Haskell programmer, this is just kind of an indicator to tell us, okay, we have seen there is a maybe as a return value, so maybe it doesn't return anything at all, but there is a do, which tells me, this body of the function already takes care of that. And then there are a few small details in Haskell that kind of make this possible. So there is a lot of details. I once heard Straustrup say, C++, you just need to understand int and vector, and then you know everything about C++, and the rest is just details. It's the same. The rest is just details. So let's have a look at the maybe. So as an example, for example, I want to make a function that just kind of can split some integer into half. So I have this function half, and it takes an integer and it returns an integer. The implementation is this is integer division, a by 2. So if I call it and say half of 8, I get 4, half of 7 is 3. Of course, because it's integer division, and half of 16 is 2. Now I want to kind of say, okay, half of 7 is 3, I don't like it, I want to tell you, because we're maybe splitting euros, and we're splitting, you two split 7 euros, you get 3, I get the other one. So maybe, I want to tell if it's not even, then if it's an odd number, I kind of want to handle this and say I cannot split it. It doesn't work. So I get this maybe, and this is kind of the definition of maybe. So maybe is a data type, and this A is it's like a template. So maybe it's like it's a template of type name A, something like that, and it maybe can take two values. It can be a nothing, or it can be just an A. And if I rewrite my function, it still takes an integer as input, but it returns a maybe integer. And now the implementation is if it's even, then I will return just and then the result of this integer division. And otherwise, if it's not even, I will return nothing. So if I try it out, if half of 8 is then just 4, half of 7 is nothing, and half of 16 is a compile error. Because the function takes an integer but returns a maybe. So I have a problem with this chaining. I cannot nicely chain it. So I would have to take half of 16. I would have to look, is it nothing or is it just a value? And if it's just a value, I can put it into the next function. So there would be a lot of kind of if handling and a lot of passes. And because this is a very common pattern in Haskell, they come up with something called the bind operator. It looks like the stream assignment operator, and it's called bind operator or bind function. And the definition of this bind operator is, you can just ignore there. I just put it there that it's the real declaration there. It just tells us there is a A, which is like a template of a template. So we have the M is kind of a template type, and the A is the nested template type. So it could be a maybe integer or maybe float or something like that. And the second parameter of this operator is a function that takes a A and returns a MB. So something like a maybe float or maybe integer. And then the output parameter of this, when I evaluate this bind operator, is a M of B. And to remind you, that's kind of the definition of the maybe. And if I look at the implementation of this bind operator just for the maybe, because this kind of, I said it's like a template of a template, there is a kind of specialization for each of these types that know this bind operator. The implementation is really simple. It's just if it's just an x, so if there is a value in it, I take this k. K was this function from a to mb, and then I just apply this function k to the value x here. And if there is a nothing in there, I just don't care what the function does and don't call it and just return nothing. So I have this if handling into this operator. And now if I go back to my function, I can say, okay, half of 16 is maybe 8. I put it into the bind operator with a second argument, another halving function, which takes out the 8 and then calculates half it, which will be just 4, and then it goes into the bind operator and so on and so on, until I get just 2. If I now have something like half of 14, then I will get just the 7, which will get into this bind operator, it will half again, and this half then will return nothing. And then that nothing goes into the bind operator with this half function, but it doesn't care about that. This will never be called, and it will just return the nothing. And now, because this is a very common pattern, there is something else. So if I now convert my code we had before into kind of this writing with the bind operator, we see I call this read moisture, which maybe returns a moisture. Then I give this maybe into the bind operator with a second argument to the bind operator. I have a function, and the function is a lambda, so just brackets and backslash is a lambda function. Then the argument for the lambda function is kind of the first thing here, and then after the arrow is the implementation of my lambda. and the lambda ends here. And what does this lambda do? It calls read temperature. The result, which is maybe a temperature, will go into a bind operator with a second argument, another lambda, which takes a temperature, because that's what's coming out here, and so on and so on. So this is just kind of implementing the same function we've seen before, just with kind of this bind operator. And now, because this is also a very common pattern that we see in Haskell, they invented this do notation. This is just syntactic sugar. It's not a statement or a function or anything. It's just syntactic sugar. And what it does is it unfolds this nesting into a kind of that you can read it like procedural code. So which makes it very nicely readable. Kind of the dark side of it, or how to call it. So there is a lot of discussion in the Haskell community, say like the do is evil, because it makes looking our very nicely functional code looking procedural, so we don't like it. There are kind of people say do is very nice, you can, for this kind of use case, you can write really nice code, and others say no, it's really evil because it kind of breaks our functional notations. But in fact it's still functional, it's just kind of, it would be just like something preprocessor-like to replace that. It's not really a language feature, how to call something doing on language level. And if I try to kind of add a main to my function to just see how this would work, I have a main, and then I call this water plant, and then it returns a maybe, and I look, is there just an amount in it? If there is, I print amount. If there is nothing in it, I print the error. Executing could be print out, yeah, I've pumped this 178 or whatever, or there was an error. And now this bind operator is implemented by a lot of classes or class types or abstract data types in Haskell. So this is a very, very fundamental concept. So there is really a lot of types that implement that. And we are going to have a look at another one, which is called either. So either is like a maybe, except for it kind of either can be a left or a right, and you see it's also like a template that has like two template types, and it can be a left A or a right B. And the convention is if there is a right in it, then it's some kind of a value, and if there's a if there's a left in it, then it's an error. And we're going to look at the implementation again of the either for the bind operator, just as a reminder what the bind operator look like and what the either definition is. If there is a left L in my either, then I don't care about the function I give to the bind operator and just return the same left again. And if there's a right on it, I take this function and I apply the R to the function. So if I give it either int in there and the function takes an int and makes a float, then I get from there, I get an either whatever error type of float out of there. So I would get there, yeah. If I now rewrite my example with the either instead of the maybe, so of course kind of this read moisture and read temperature and pump functions, their signatures have changed because they don't return a maybe anymore, they return a either, which has a like the read moisture return either of an error or a moisture. So there is either a moisture value in there or there's kind of an error type in there, whatever the error type is. And if I look at the implementation here, just the signature also changed because it now says instead of maybe I return a volume, it says I return either an error or a volume, but the implementation is still the same because this is kind of the concept that we use, this kind of a higher abstraction level. I just changed the type, but the implementation didn't change at all because it still can apply the same principle and concepts. So I just had to change the signature, and of course the implementation in there where they really return something, but kind of the usage is still the same. Now if I would have a main for that, it's kind of still the same. It says, okay, I call this function. If I get the right amount, I print the amount. If I get the left error, I just print the error, and it may look like this. It's the same as before. It's kind of, if it goes, it's okay, I get the volume back. And if it goes wrong, it could be that this error type has kind of description or whatever in there, and then I get kind of nice error message. Now, if you're going to look a little bit further, who has done some Rust programming? Oh, quite a few. So you maybe know the option, which is basically kind of the same thing as the maybe. And then there is the result, which is, I think it's something very fundamental to Rust. It's used a lot in the standard library itself of Rust. And it just tells, it's kind of like a templated enum, and the enum it's like enumeration, can be either can be this or this or this. So there are two kind of enumeration values, okay or error, and they can hold values in there which are of type T, which is kind of the result type, or an error type. So this is more or less basically the same thing as the either. And how does that look if I use that? So if I'm going to use it, I call my read moisture function, which will return me a result of a moisture or a string. So the error is just a string, and it will assign that result to moisture. Now the result can be either okay or it can be an error. If there is a okay in there, it takes out this value, this moisture value, and just assigns that to the moisture. But if there is an error in there, it doesn't really assign to the let moisture is kind of assignment. It doesn't assign, it kind of jumps out this match statement with the return, and because match is just a statement, it's not a scope, it doesn't return from the match, it returns from this function here. So if I get an error there, this whole water plant function will return with the error, and then it goes on and reads out the temperature. If there is something wrong, it will jump out from here. In the end, it's just that's a little bit Rust specific. There is no assignment, and this is not a fault in my slides. There are no semicolons. This will just tell me, like, the return value of this statement here is the return value of the function. That's something Rust specific. And this will just tell, okay, I call the pump, and then depending if the pump is okay and I don't care what's in there because pump had no return value, I return the amount, and if there is an error in there, I return the error. So there is no return written here, but it's doing the return here. Now you see, this is kind of, here you have always to write the kind of the same pattern. It's very tedious to write that. It's always calling it and assigning it, and before assigning, evaluate, is there a value I can assign, or do I have to return with an error? And because that's so common, they came up with this operator, and I just say I want to assign to this moisture value the result of this read, and I get there a question mark, and this tells if there is a value in there, then assign it to the moisture. If there is an error in there, just return with the error. So I got rid of all this kind of error handling, and it's just there. And if I would kind of try it out with a main function, I call it and I look, is there an error amount, and I print something. It's the same as before, and I maybe get this nice error message out of the string there. Now back to C++. In C++ 17 we got standard optional, which is kind of almost the same thing as a maybe, or something similar as the maybe. So I could implement my function with maybe. So it doesn't look that bad. I call my moisture sensor read function, I get an optional moisture back. I look, is the moisture valid or not, and if it's not valid, I return kind of I return the null opt is the nothing, and return nothing, and if it's okay I go on, and then I calculate and use the values I got here, and so on. Now we could also say, okay, we want to have a nice error message. We want not just get there nothing happened, we want to know why. And then if we want to use something like the either from Haskell, we have the standard variant which could be used to implement something like a either. And I now just defined like the read of the moisture sensor returns a variant of moisture and error, and the pump returns a monostate, which is kind of it. I don't care about the result. It's just it will return it's okay or not, but there is nothing in there because the pump had no return value or an error. And then if I look at this kind of implementation, it already gets a little bit of noisy. I kind of have to check, like with the standard get if error, is there an error in it, and then I return this error and have to dereference it and so on. So it's still kind of readable, but it's already a bit of noisy to always do kind of this evaluation of the error. Now when I use a standard variant, then the standard visit cannot be far. That's kind of, they're very close friends. They like each other. So if there is a standard variant, there must be a standard visit somewhere. And the standard visit is kind of it's a visitor pattern. I think it's not just for the variant, but that's kind of one use case that you can put in variants, and then you can have a different visitor depending on what is in your variant. To kind of nicely use the standard visit, this is something you don't need to remember this template here, but you should remember that you can find it on CPP reference on the documentation for standard visit. This is kind of important that you can nicely use it with lambdas. And then I have another helper which is just kind of, I defined this kind of result volume, which means, or the amount, which is a result of volume, and the result of volume is a standard variant of what's in here, which is then the volume and an error. So if you see something in the next code, if you see amount, it would mean it's a standard variant of volume or error. This is just that the code on the next slide is nicely fitted on 3 lines or so, or almost. This looks really scary. So to be fair enough, standard visit has really good use cases, and it is a nice thing to look. If you want to know more about how to use standard visit and variants for use cases where it really fits nicely, you have to look up on something called value types. I think there are a few talks on conferences at the moment that talk about value types. There you can get some nice ideas. Here it didn't really help with the problem. The code it's kind of get this nesting. There is kind of, it needs a lot of typing, and it's not really readable in that state. So to just give an overview of what it does, if you look at the top line, I read out the moisture sensor, assign it to a moisture variable, and then I call this a return on this standard visit with kind of one of these helper that I can put in lambdas. And the second argument is the moisture. So the moisture on top, moisture sensor read, is here. So it's the second argument of the first standard visit call. And then the second argument is kind of struct with 2 lambdas in it, and 1 lambda is to, when there is an error in it, I will do what's in there, and if there is a moisture in there, I will do what's in there. And the error will just return amount error, so it will return kind of the error. It will propagate the error it got from the reading the moisture sensor. And the second lambda is then just kind of the same thing. In there it will read out the temperature, and then the same kind of game starts again until we kind of are in the inner scope where we have called the pump, and then look if there is a pump error, we return an error, and if the pump went okay, we can really return the amount. Now I could say, okay, I always had to kind of, I first called the the readout or the action I wanted to do and put that in a variable, and then in the end I put the variable in here. I could say, I could directly write it here. So it gets a little bit shorter, a little bit nicer. I have the interesting code is all in one place, but unfortunately it's backward. So it first reads the moisture sensor, then the temperature sensor, then it does the calculation. The last step is to pump. And up there I have the whole error handling. So it didn't really help that much. So this is not so nice. And if we just look how we could use that in a main function, it's the same as before. What we can see here is maybe this is now somehow of a better use case for the standard visit. It was not kind of to try to chain all this sequence of actions. It's more like I have one call, and then depending on what the outcome is, I want to do either printing out the value or do some error handling on whatever, and then this kind of starts to look nice because there is no nesting. And if I could do maybe write some nicer code what to do there. So before we've seen in Rust there was this result type, and now we could kind of start to mix things together and say, okay, I have kind of this either, and I like the idea that I can return a value or an error, but the syntax is kind of not so nice. But there was this Rust type, this also looked kind of nice. Maybe I can mix something together. This is kind of a class you need to kind of get your do-it-yourself result type. This class is really very simple. Most of the stuff is just kind of, I have a function to call, is it an error or is there a value there, or is it an error or okay? It's kind of a little bit like the Rust syntax, and it's just kind of compare something. So it doesn't really operate on the type anymore, but on this index. This is just because this result type could also handle the case where I say I want the result of integer, or I want the result of string. And then I cannot differentiate on the type, then I need to go onto the index of the variant. But kind of this function is really, it's just a kind of it just forwards kind of this comparison. And also getting out the value is just kind, you can get out a reference to the value, and it's just kind of calling this standard get. So it's just kind of a small wrapper that there is no logic in it. The only kind of difficult thing is the constructor up there, which uses some sphinx. It maybe could get nicer with concepts, but it's also not that complicated. All kind of what this template does, or kind of this standard enable if does, is it tells the compiler that I only kind of can use that constructor if I can use the constructor of standard variant with the same arguments, because the constructor of standard variant already does what I need, because I'm using the standard variant to store my result value, and it's just when the constructor of standard variant is quite complicated. If you just look at the definition on it, there are quite a few restrictions, what it can accept and not. And this is all implemented at the moment, for example, in the GCC standard library with sphinx, and it's really huge. But I don't have to care because it already can it, so I just tell it, use the same. If I can make of my value, if I can convert it to a standard variant, then you can also make a result. Except for one exception, which is here, to say I don't allow kind of putting a standard variant in there. That's to kind of, that you cannot get confused and then kind of put the wrong thing in it. So that you cannot directly assign it, kind of say, okay, I know the result just accepts a variant and I just directly put the variant in there. That's just to prevent this one, that the interface stays clean. And then there are two kind of friends which are just kind like the make unique or make shared. They're just make okay, make error. They're also not that complicated. It's just a little bit complicated because you cannot use the types to find out what to call. You have to use the index. but it's just calling, kind of creating a variant or a result and putting in the variant type and return that. If I now rewrite my code with using my do-it-yourself result type, kind of, I still have the ifs. I call read out my moisture sensor. I see, is it an error? If there is an error, I return the error. And if it's okay, I later on can use the value. But the code got much, much cleaner than when I was using the standard variant directly. So this is kind of, this is the place where I arrived. I said, okay, this is really nice to use. This is something I want to try out, to start using. So I got rid of the kind of the output parameters. If I call something, it tells me there is an error or there is a value. And if I get an error, I know I don't have to care about the value because there is no value. And if I get a value, I know I don't have to care about the error because there was no error. And it's not kind of a mixture of these concepts. And if I kind of apply this in the main function, it's the same thing. I call this water function. I check, is it okay? I print out how much I could pump. And if it's an error, I print out the error message. Now we could theoretically go a step further and say, okay, in Haskell we had this nice bind operator. Why not try to use the bind operator in C++? Now this is a very naive implementation of the bind operator. It kind of works, but it accepts things it should not accept as a bind operator, so it's too forgiving. If I want to kind of start restricting it and say you have to comply with what the bind operator is in Haskell, then I still would have to add a lot of Sphinx code that I don't want to write at the moment. So this is just kind of a proof of concept. So we have the bind operator, which is kind of, when it's called, it just checks if the value, is it an error? If it is, okay, return the error. If it's okay, then I have kind of this template funcF, which is something that is callable, and I just call this f with my value in it. Like the second one, maybe you had seen it in the code before, it's the same as the bind operator without the assignment. This is used, for example, for the pump, which had no return value. This is just like a variation which on the error it does the same. Is there an error? Return the error. And if there is a value in there, I don't care about the value and just call the function without the value. So the difference is only there I call my function with the value, and here I just call the function and don't care about the value. And if I rewrite now my code from before with my do-it-yourself bind operator, it's got much, much shorter, and there is just return moisture sensor read. So I get this result type, which is a moisture or there is an error in it, and I put it to the bind operator, and the second argument is a lambda, which takes like this moisture value, and then in the lambda I read out the temperature sensor and then put that in the bind operator again, and so on. So we have already seen this. So this is basically the same. So the syntax is a little bit different. There are more returns I have to write here. They're kind of implicitly there, but it's kind of reading out moisture sensor, calling the bind operator with a second argument, the lambda function, which is also a lambda function there, which takes the moisture, and the implementation is kind of reading out the temperature. So basically this is the same. And because this is the same, so we have seen before with the do notation, we can make it look nice. So what if in C++ we could also add something like the do notation and kind of rewrite that stuff up there into the same as the Haskell code, which then would look like something like that. But unfortunately, I don't know how the wizard notation and the unicorn operator should look like, so this is kind of the barrier or the wall that I hit, and I couldn't get further. So if you have an answer for me, I'm open. Yes?
You can actually implement it for GCC and Clang with macros. You can have a look at Boost Outcome, it is called, I think. Which is a library which basically implements this, and they have an implementation for GCC and Clang where you have a macro which basically does the same thing as the question mark operator of Rust. So you have to, I think it's called try, boost try or something like that. I'm not sure. And you as a parameter you pass in your code, and either the code returns immediately, or you get the OK state as a return value of the macro.
Yeah, that's true. With macros, you could do it in the Rust way, or you could even write a variadic macro which kind of does the do notation of the Haskell function. I didn't want to mess with macros. I'm very afraid of macros because I once worked at the semiconductor company, and I was working at the compiler and debugger tool chains, and we had kind of the compiler writers there, and they were very afraid of the preprocessor, which I'm also very afraid of. If you're a compiler writer, it's the worst thing you have to care about. But it is doable with macros, that's true, yes. And that's also what I think, these concepts, there are implementations out there for use, and they go then the macro way, because that's how you have to do it, that you get rid of all the noisy syntax. So what did I learn from this whole kind of theoretical exercise? So the first thing I learned, that maybe either I'm going to look for a new job as a Haskell programmer because it's nicer there than in C++, or maybe I spend more time with C++ meta programming, that I can appreciate it more and maybe get better solutions. So what I really learned, or what I would like to give you as I would like to give to you from this talk is, I didn't really mention it explicitly, but I made a lot of use of value types. So this is really something to look into. So if you start using concepts of value types, you can start to make your code express better what it does. So for example, the functions, they return the moisture. They didn't return an integer. So you just don't call it and get an integer. You know what this integer is. But there is also, like, because I use this result, and the result is either an error or a value. I don't have to care of kind of this kind of state where I don't know, is it now, what do I have to do if there was an error, is kind of what I got else, is this valid or is it not valid? And since yes, I know it's partially formed, but what can I do with that information? And you can make, especially if you make interfaces, you can kind of, or APIs, they can be much more expressive just from the signature of the declaration of your functions or your methods. You can already see what they're trying to achieve. If you just see there are output parameters and maybe Boolean or int return, you have to kind of look it up, what does it do? And if you use kind of this kind of approach, you can already make your functions, like, tell the user of this function what is the intent of it and what can you expect of it. Of course, it comes at a cost, so you always have this kind of, you have to decide for yourself, do you want to have this cost at the kind of the value that my interface gets nicer. The second thing is that especially with standard variant, you can kind of prevent this kind that you have meaningless states. So it's not that you have kind of, you get back a value and you get back an error, and then you have to figure out, you get back either a value or either an error. But if you have a value, you don't have an error, and if you have an error, you don't have a value. So it kind of gets rid of this impossible state. So this is also something that comes up with these types here. If you look at sum types or value types, or not sum types or product types, what kind of is there? And then the third thing is kind of what I was really surprised that when I made up this result type, that it was not so difficult to write this wrapper. The hardest thing was to understand, don't be too clever yourself. The standard library is already really good. So if I want to, there is already the standard variant, so I can use that. So I don't have to invent the constructor that is so clever as the constructor from standard variant. It is already so just use it and just tell in the wrapper, do the same thing as the constructor would do of standard variant, and you don't have to kind of care that much. So don't try to be clever, but kind of don't be afraid to kind of write these wrappers for yourself, so that you can reduce, I call it syntactic noise, that you can get rid of this stuff that kind of pops up and is not really interesting. You just have to do it because the syntax is like that. I mean, the C++ standard library syntax is there to kind of enable you to use it in most ways as possible, kind of to enable you to do something. But for your use case, it then maybe makes sense to kind of make your context smaller and just write some wrapper code that you only can use it for the way you want to use it in your concrete example. And then the last thing is keep your eyes open and discover all the functional stuff that's popping up in a lot of programming language lately. So there's a lot of fuss at the moment about functional programming. And if you learn a functional programming language, then it will maybe also get easier for you to discover and see, that's a concept I know from functional programming. Yeah, questions? Yeah.
The first question from Paul Bendixson is, what about the expected and outcome types? This would allow us to use if moisture instead of reinventing it yourself. I haven't looked at this type yet. So this is, I know they exist or start to exist. I don't know, does somebody know? I think they're going into C++20 or... I'm not so sure about, but that's kind of a next step to look at what's there. Yeah. The second question is, deep nesting is usually a code smell. Why should it be better to have all these calls inside each other than putting them in variables?
Yeah, the trigger for why would I want to do this was often, especially I think in embedded programming, you have kind of a sequence of steps, and you want to have some place in the code where you can read the sequence, what it's intending to do. And this was kind of the trigger of the whole discussion, that how can I write this sequence that I see, okay, it's reading out this, and then it calculates something, and then it does the pumping in the end, without having all these breaks with ifs in between or whatever, to kind of, that I don't have the sequence anymore in a kind of nicely readable sequence. But of course, yes, there are other approaches to do that. Other questions?
Could you have a look again at your Haskell operator implementation in C++? I'm not quite sure if I have a question there. You did this by
and it's really just a very naive implementation.
Yeah, but Couldn't you just like use it without the lambda and just call the normal function? That should normally also work, then it would probably just look nicer. If you now skip to the moisture example.
No. Because I read out the moisture, and I read out the temperature, and these values are used by the calculate amount.
I would have a solution to that problem if you like take another operator which takes a tuple of them and expands them and will call the both functions, then you actually could solve that problem and just have those both functions called. Like, yeah.
That's it's kind of like the first thing is if always the next function you call takes exactly the output of the function before as an input, you can nicely chain it without need for this bind operator. But if if it gets much more trickier, if it doesn't really match to that you have this nice chain. Also what you said, if you have functions like this, I get one value and another, and then I get a function which by accident really just needs these two values. Yes, I could go with your approach, but the Haskell way, because it's such fundamental concept, it's on the general case, and you don't really know what this relation will be much more complicated. It's not just you have first you gather some input, and then in this you get this input in the same order to the next function. So in the general case it doesn't work anymore. For if you can say I can live with that way, that either I just put it into the next function, or I can gather all the values and then put them in the next function in the same order, then it works, of course. Other questions? Then let's go to the break.